we today start a new topic. As you can see, is the topic is air pollutants. Air pollutants say this is we have known somewhat about this air pollutants. As you know, mostly the air pollutants that we have discussed are say all these gases like SO2, CO2, then NO2, and then finally also we have discussed about the particulates RPM and SPM. We have also understood the standard of this. Here in this case, it would finally we would discuss that what would finally lead to the dispersion of air pollutants, how these air pollutions actually disperse across an area or across a particular atmospheric column. So what we try to know is, as you can see, if you can observe now, there are a few things very important in this case of meteorology. Why these air pollutants are one thing. The meteorology would discuss about say the temperature differentials in the atmospheric column, temperature differentials in the atmospheric column. And secondly, we can also find that is we can also observe say the pressure difference and also the third thing that we can find out, this is a wind direction and velocity. So wind direction and velocity. So where you can see these three important parameters. Apart from that, you can also discuss about say this diurnal changes in the temperature, moisture, etc. So this are diurnal changes in the say day wise changes during the different times of the day and different times in the night, diurnal and nocturnal changes in the temperature. That all these things actually influence the flow and concentration of the pollutants in the atmospheric column. So we would have to discuss. So in cases how these air pollutants actually, this would help us to know, if we know about the dependence of these air pollutants and regarding their movement of in the atmosphere, it will help us to know the mechanism by which the pollutants will spread in the atmosphere as well as their settling characteristics, right. Secondly, another important thing that we can find out is this, the atmospheric atmospheric travel of the pollutants, atmospheric travel of the pollutants atmospheric travel of the pollutants, as you can see. So, the first thing that you can see, the mechanism by which the pollutants will spread in the atmosphere, as well as their settling characteristics, how they would settle and how they would travel. These two things are of extreme importance to us. And we will also see this, atmospheric travel of the pollutants, and also atmospheric travel of the pollutants. You can very well see, particularly if you can observe the situations like, during the cloudy day, if it is, at the end of a cloudy day, you will find that the air almost doesn't seem to move. It remains a very the air seems to have stopped in situations like this, and the heat remain confined within the very short atmospheric column. I mean, within the cloud and between the cloud and the earth. So, that gives out to different kinds of discomfort. So, this discomfort, and then when the sky is clear, the comfort level increases. All this, this atmospheric changes has something to deal with the travel of the pollutants at different levels in the atmosphere. Okay. So, this atmospheric travel of the pollutants, and also the immediate the character of the immediate atmosphere above the earth, right, above the earth. So, immediate atmosphere above the earth, it is of great significance. It will have great significance. We will try to see how and why these things matters a lot. Okay. Now, before we further go on to this, let me explain further on this, about this, what are the typical things that we generally observe is that, with the one very important topic here to discuss about this adiabatic lapse rate. The adiabatic lapse rate. We will come back to this. I am going to define this, mathematically. This is adiabatic lapse rate. The adiabatic rate deals with decrease with altitude, deals with the decrease in temperature with altitude in the atmospheric column. The adiabatic lapse rate deals with the decrease in temperature with altitude in the atmospheric column. So, let us starting, what we generally try to begin here to understand is that, there are the typical phenomena that takes place. The typical phenomena that takes place is that as with the altitude, if you just observe this, if you just observe a particular balloon here, if you just observe the balloon here, and the balloon here at this point of time, you will observe that the balloon would be generally, what would happen is, here there would be this, in this case of the balloon, as you can observe here, there would be, this would be at a higher pressure. So, you can, this, if you can just observe this P1 here and P2 here, you can see, find always P2 becoming more than P1, more than P1. So, what it will happen is, as this would make it to, as you can see this P1, it would make it to expand. As you can see, it will begin to expand as the pressure would be less, the pressure would be less, as a result of which it would begin to cool down. As it will begin to cool down, so there would be this, particularly as on the other hand, at here, as you can see, remaining under pressurized condition, this would be, this is how this P1 here under that. So, this here you can see the temperature here if you can see T2 and T1, you will also find that T2 becoming, this is P2 is T2 becoming more than T1. So, here, as a result of which, this is particularly, so we would consider, we would just use this analogy, to consider how this, particularly the cooling and the how this. So, what we can observe here is, if you just observe a particular column of air, if you are just observing a column of air, so it would continuously, it is as it is going here, you can see, say, T1, T2, T3, we can see with altitude, T1 is T2 is T3, like this. So, you can see with altitude the temperature actually changing. So, in the altitude, as you can see, in most cases, as you can see within in a column of air, enclosed column of air, we can observe that the temperature along the atmosphere, along the altitude, this temperature would begin to decrease. So, this being a very typical phenomena, but how this rate takes place, what is the change in the rate that takes place. So, we can observe here, is a particularly, as you can see here. So, if we will observe we will consider the concept of air parcel, is generally considered as imaginary entity of air being made up of a number of air molecules but not vapor, imaginary entity of air being made up of a number of air molecules but not vapor. Remember this, with an imaginary boundary around them. Them means the particles, there is the molecules, they are molecules. So, here we can see this, trying to understand this from this adiabatic lapse rate, that we can generally observe now how we can find out the rate at which the temperature change in temperature takes place along the altitude. So, we can see this in the particularly following ideal gas law, and first law of thermodynamics. First law of thermodynamics, say there is thermodynamics, that is conservation of energy. This is first law of thermodynamics. We can find out, we can write an expression for this air parcel. We can write an expression for the air parcel which is known as, which is equal to Cp into dt minus V into dP, where dq will be heat added. Remember this, heat added to the parcel, per unit mass. This is per unit mass, it is in joules per kg. This is important, you must, I try to underline this, per unit mass. I will tell you why, per unit mass, okay. Per unit mass is this, Cp is a specific heat, at constant pressure, dt is, so you can see that is the amount of heat required, heat required to raise temperature of 1 kg of air by 1 degree centigrade, while holding the pressure constant. And the Q is equal to, for air we know it is about 1005 joules per kg degree centigrade, okay, joules per kg degree centigrade. So, see, this is Cp, which is nothing but specific heat at constant pressure, okay. Cp at a particular pressure, say we consider this to be 1005 joules per kg degree centigrade. About this, we can also find out here, this is the dt is incremental temperature, change, incremental temperature change in Kelvin. K, V is the volume per unit mass, and dP is incremental pressure change, incremental pressure change, we can say that incremental pressure change in pascals. So, here what is observed here is, as you can see, essentially So, here as you can see this is a very standard equation as such. What is essentially is a dq plus b dp is equal to Cp is equal to Cp into dt. What is this total heat added? Heat added, the first equation is heat added in the per unit mass. So, it has to be basically multiplied by m, as you know that m into Cp into dt, that is the temperature change, isn't it? So, is no. So, this mass has come down here. So, that is why it has become per unit mass. So, okay, similarly as you can see this VdP volume per unit mass and this incremental pressure change in Pa. So, there are two changes that would take place here, as the heat would be, the heat added to the parcel would be essentially Cp into dt, but there would be some pressure that would be lost in the volume per unit mass and the pressure, incremental pressure change. So, mass into volume. So, you can see here, so this would be, this is what is to be reduced from this Cp into dt. Total transfer of heat would be this minus this one, this would be absorbed as a work done, and so this would be the net heat added to the process. Okay. Net heat added to the process. So, as you can see this is a perfectly a non-adiabatic process. Here as such, if you just can consider if the process is considered, the process is considered to be a case where there is no loss of heat, across the boundary of the parcel, as across the boundary of the parcel, that is as if the parcel is covered with an insulation which does not as if covered with an insulation which does not allow the heat to enter or exit enter in or exit from, that which does not allow the heat to enter in or exit from the parcel if the process is considered to be a case where there is no loss of heat across the boundary of the parcel, that is as if the parcel is covered with an insulation which does not allow the heat to enter in or exit from the parcel, then dq is equal to 0. If dq is equal to 0, we can very well write this equation, if we just the above equation, that is dq is equal to Cp dt into minus v into dp, that we can very well write as dt by dp is equal to v by Cp. So, if the top equation can be written 1, this one is 2. Okay. So, now here Now, this is a condition in a particularly a situation when there is an adiabatic case, and which we consider that there is no, this has taken place without any heat being entered into the parcel or exited from the parcel. Still this two work has been done, I mean complementing each other. In such a situation, so there would be this, if we just, this can be explained like this. Okay. Having gone from this, now if we just try to understand the situation physically, how it happens, if you can observe things like this, here, if you just observe that this column of this, particularly the parcel is, if the parcel is in a perfect equilibrium, say this parcel is in a perfect equilibrium, that means the parcel is in a perfect equilibrium, there is absolutely no movement of the parcel at this point of time. We just consider that this parcel, as you can see, this parcel is a volume that I have said. You cannot see the volume as such here, but what we are observing here now is this, says unit volume, which is unit volume. Say we are seeing just a face of it. So here, if you are just seeing this face of it, here what we observe is this one is, say this one is the area A. If we can say this is the area, the total area at the bottom, as you can see here, this total area here. So this is the area we are talking about. This is A. This is the area we are talking about. This total area is, this one is, if you just observe this is A. Okay. If this area, so when it would be actually, so there would be, as you have observed, say the pressure on bottom, as such, to since the pressure here would be, there would be always a pressure on top of this, this one is Z, and this one is, this is pressure from the top, this is pressure on top is equal to P, pressure on top is P, and the pressure on the bottom is equal to, say, P plus G into rho into dz. Okay, here, so as you can see, this is the G is the atmosphere, I mean this is acceleration due to gravity, as you know. G is, says rho is the density, and dz is this, this particular dz, okay, a particular part of the column. So here, as you can see, is that a horizontal slice of air, it is a static column that is in equilibrium, and they say this slice of air with column thickness dz, density rho, density rho, and we will be having, and this is mass is, as you can see, the mass is equal to rho into A into dz of this mass. Having said this, one thing we can very well write here, as you can see, this one is P, this is pressure on the top, is not rho, remember, this is P, this is P, this is P plus G into rho into dz, as you can see here. So if it is has to remain in the equilibrium, what it should be, you know, this is Pz, this is Pz, sorry, this one is Pz, and this is Pz plus dz. Pressure on top is Pz, and this one is pressure on bottom is Pz plus dz. So this one is, if you can observe this, as equal to P we can write an equation as such as like this, you know, Pz, as you can see, this one is okay, I mean, since it is multiplied by mass here, as you can see, this is mass, so the mass into this is the weight divided by A. So you know, A cancels here. So it's not necessary, you can very well write this equation also here. So this one also can be written as like this. So here, so if this is, just 1 minute, this one is, let me make this clear here, Pz plus, no, it's okay, the pressure on top is this, okay, as you can follow right this, you know, you can see this Pz, it has to remain in equilibrium, it has to be countering this, plus this one, plus this column, G rho A into dz divided by A. This one, if you can just see this, you can also write it like this, this is Pz, the dP is equal to, change in pressure would be basically so if this can be, if these two things are, you know, if they are Pz, if we are just changing it to say this one is place P is P dz minus Pz plus dz minus Gp A into dz divided by A cancels. So we can find out this, or dP, or we can write this dP, this is the dP is equal to, this one is minus Gp dz, or else we can write it out very simply as this, or we can write dP divided by dz is equal to minus G into rho, right? This one is rho, I am sorry, this is rho. Needs to be, you know, just it's not a, I mean, I wrote it wrongly, it's P kind, it is rho, essentially rho, as you can see this. So this is minus, as you can see, the minus is just to indicate that with altitude the change in the pressure, it would be minus, so it would decrease, just to ensure that. So these two things can be explained. We are, as we bring in a new term, that is about dt divided by dz, dt divided by, if what is that says, this is a new term, the rate of change of temperature, rate of change of temperature in Kelvin with altitude. With altitude, we can very well write this as dt divided by dp divided by dz. You see here, what we have just done is, the divided and multiplied by the same term. What we have done, the simple operation that we have done is, we have multiplied and divided by the same term. So you can here itself, we have found out dt by dp by dp is equal to v minus cp under adiabatic condition, and this one is equal to, we have already found out g into rho. So this one is the equation number 5. This is equation number 5. So this is equation number 5. So this, if it is now, as you can see, this is v into rho here, v into rho, essentially this one is minus, there would be a minus here, this is minus, this minus gp, this is minus g divided by cp, because g divided by cp, because this one v into rho is essentially 1. If it is for considering unit volume, considering volume per unit mass. Considering volume per unit mass, if you just see this volume per unit mass multiplied by mass divided by volume, that is a rho, so it actually cancels out, is equal to 1. Is that all right? So this one is volume per unit mass V, since V is volume per unit mass, and rho is there basically mass per unit volume. So each cancels out and this becomes 1. So we can find out this, if we can write dt by dz is equal to minus g divided by cp, As you can see in the first case, if you just give the value here, say this g minus this g is equal to 9.806 meter per second square. That is typical value of g that you know of, and this one is, I have already said cp is equal to 1005 joules per kg degree centigrade, is equal to, so is basically, if we are just making a conversion here, 1 joule divided by kg mass m square by second square, if we are just trying to, this kg comes on the top, so the 1 joule gets changed. So if you are just making a change in the unit itself, it is taking place is equal to what we find out is 0.00976 degree centigrade per meter. What I am trying to do is, we are just trying to kg degree per centigrade. This one is, if you just convert the units into joules, joule if you change, and if you can just if you just change these joules into these values here, you can very well find out that all these things cancels out, and degree centigrade, this one is degree centigrade, this degree centigrade goes on the top and divided by meter, this remains. So here in this case, as you can see here, so what it says is a very interesting observation that it makes. If you can just observe this, or we can write as dt by dz is equal to minus 0.0976 degree centigrade per meter, is nothing but, if you are just, is about 9.76 degree centigrade per kilometer, multiplying both by 1000. So it becomes 1000 meter become 1 kilometer, this one becomes minus 9.76. So, or this is what is known as the adiabatic lapse rate. This is adiabatic lapse rate is generally known to be is 9.76 minus 9.76 degree per kilometer, or equivalent to, we generally observe it as 10 degree, we generally say it is a minus 10 degree centigrade per kilometer, or or you can very well write that as dt by dz. With a little bit of approximation, we can write this to be 1 degree centigrade per 100 meter. Okay, this is the dt by dz. So what is interesting here is, if you just consider this, as temperature, if you just temperature and altitude under a perfectly adiabatic process, the curve would be like this. The temperature would continuously begin to go down. So this is about minus 1 degree centigrade per 1000 meter. So this is on this slide, we will now explain how this atmospheric changes essentially take place. So what is happening here is, in a situation like this, if you just observe, there are two conditions that we can discuss here. This is known as the curve of adiabatic lapse rate curve. Adiabatic lapse rate curve, okay, which it signifies that with height, with the temperature, with altitude, there would be almost a linear relation to exist in under adiabatic condition, when the with the temperature would begin to decrease. When the temperature would begin to decrease, we can, from this we can establish two important relationship. One is the stable atmosphere. We call this, that the stable atmosphere. The stable atmosphere. Just to explain the situation, if the parcel, if the same parcel, if the parcel at higher elevation, at higher elevation is now colder than its surrounding, than its surroundings, it will want to sink back down again. Begin to sink down, or this is will begin to sink down again. So this if the parcel at higher elevation is colder than its surroundings, it will want to sink back down again. So whatever would cause the parcel, see this, whatever would cause the parcel to move up heat content or so whatever would cause the parcel to move up will be resisted by the atmospheric condition, by the atmospheric condition resisted by the atmospheric condition to bring it down. If this, so what I am trying to say here is, if the parcel at higher, so what is happening is, suppose a body of a parcel having say some heat content in it, it is it is a hot air, suppose a hot air. So as we are saying is, as the hot air would begin to go up initially because of its buoyancy, till at a point of time when it will not further like to go down, it would, as it would be coming, it would be colder, then it will begin to go down. This situation, if in the atmospheric column exists, the atmosphere would be called stable. That means whenever when the balloon or a particular parcel of air is moving up under adiabatic condition that we have considered so far, so when it is going up like this, there would be always a temperature change. I mean the temperature reduction would take place, and this temperature reduction would, whenever there is a relative difference between the atmosphere and the parcel would go up because of the temperature being more, and the air becoming lighter than the air on the surrounding becoming colder as it would take place over the column. So after a certain point of time, when there would be the temperature inside the air parcel would be equal to the temperature outside in the atmosphere. The movement would be stopped. It would come to an equilibrium, and as such, at that point of time, due to mass, it will begin to come down. That is why all the balloons, as you can see, all the balloons after certain time, due to hot air balloons, after certain time it begins to come down if the source of heat is stopped, the source of heat is restricted. So here, if this happens in the atmosphere, it will be called as a stable atmosphere. It is known as stable atmosphere, where it allows us, so see, if you just trying to understand this situation like this, if you see this in the environment here, say there would be a parcel, these parcels depending on their thermal content, they would undergo a attraction below. Their upward movement would be restricted at a one point time in the altitude. Then this would be, if depending on the thermal condition, at one point of time there would be a downward movement of the parcel. But remember, all these parcels would not, I am not telling that at all equal height it would happen. It would not happen, because all of them are having different thermal contents. So, but if this phenomena across this atmosphere takes place, this atmosphere would be known as stable atmosphere. This atmosphere would be known as stable atmosphere. On the other hand, if this situation does not prevail, well, the parcel would continuously, this parcel would begin to go up. This parcel would instead begin to go up in the, due to different changes in the atmospheric condition. During the different changes in the atmospheric condition, the atmosphere would be called as unstable. That means, unstable means some atmospheric changes have taken place that has changed the way the atmosphere should behave, normally should behave. The normally should behave means, it would follow an adiabatic lapse rate, isn't it? It would follow an adiabatic lapse rate if there is no change. But if there are sudden changes due to temperature differences during the daytime, during the different changes in the summer, during the winter, there would be all changes taking place in the atmosphere, and thereby when there were this situation of this adiabatic lapse rate, following the adiabatic lapse rate, and the parcels would undergo a situation when they would be continuously rising, or they would be continuously coming down. In such situation, we would call the atmosphere to be unstable. We will come back to this, in the next class itself. Okay. So 5 minutes. So, okay, we were discussing about this stability in the atmosphere, and so we just discussed about one important thing, that is, I said that if we consider that the two situations that we have explained here, say if is, as you can see, is if the parcel, as I have said, that parcel begins to move, the parcel begins to move, and then at one point of time the parcel begins to sink down. So, if the sinking down, as you can observe here, this is how it would look like. the parcel would begin to sink. The percent would begin to sink. So, you can see this, instead of say having to go up there, so this is how the parcel is moving up. The parcel is moving up at this point of time. At this point of time, as you can see here, at this point of time, this the internal parcel temperature, parcel temperature becomes fast equal to the external atmosphere, the internal parcel temperature becomes fast equal to the external atmosphere, and less due to the atmospheric condition, becomes less due to atmospheric condition. The Earth's surface becomes cooler than that of the air on top of it. Okay? But this reduction, particularly this characteristics begins to change after 2 a.m. it becomes the most pronounced effect. After 2 a.m. about 9 p.m., 9 p.m., 6 p.m., 3 p.m. we can observe this would remain like this. But on the other hand, in the 3 p.m. side, as you can see, we will observe that it would almost be close to adiabatic lapse rate. This is known as the radiation inversion. This radiation inversion, there is another kind of radiation inversion that we generally observe, for your example here, that is particularly in the situation of, in the case of say height, this is altitude, this is altitude and temperature. If you see altitude and temperature, we observe that at about 10 a.m., the inversion is like this. It's about 10 a.m. at about 10 a.m. Whereas the adiabatic lapse rate is essentially this one. This is what is, these are the things that take place. These are the things that are known as the inversions.